はい、それでは、ホルナゲル先生にスピーチしていただきます。ホルナゲル先生は、レジリエンスエンジニアリングの創始者で、もう私が、くどくど言う必要もないほどの、超有名人でございます。本日はですね、フラムのモデルから、それを解釈する方法を自動生成するという、全く今までにない新しい、機能を、開発するというところのお話をしていただきます。言ってみればカオスをですね、解釈する方法を、示し始めたという画期的な、お話です。Erik, please start your presentation.
Good. Thank you. Thank you. Good morning to all of you from Denmark. I'm sorry I'm here and you are in Japan. I would rather be in Japan, and perhaps you would rather be in Denmark, where the weather is gray now and it will rain today. Anyway, I'm very pleased to be able to make a presentation to you today about the FRAM, or relating to the FRAM. It is not a presentation about a use-specific case or use or analysis made by the FRAM, but it is a presentation about some developments in the FRAM. And as you can see from the first slide here, we have been working on something that we call the FRAM Model Interpreter, and this is what I will be talking to you about. You all know that we can build FRAM models, and that models can have many different sizes. There can be small and simple models, and there can be large and complicated models, and I have just shown two examples here. The problem when you build a model, of course, is always whether it is correct. Does it actually describe what you would like to describe? And so the question is this model correct? Does it work? Will it work? Is it what I want to have? And we know when we talk about models in general, people talk about models being validated. You can say it's a valid model of something, but in the FRAM, we talk about models being calibrated, but not validated. You can never validate a model and say, this is a true model of the phenomenon or the activity that you are trying to describe, but you can calibrate it, which means that if people who know about the activity agree that this is a fair representation of the activity, then you can say that you have calibrated the model, and you can rely on the model. It's a fair representation of what's going on. But we would like to go a bit further. We would like to find out whether a model actually works. And the way we do that so far is, if you take the one on the upper left-hand corner, is that you sort of think through it step by step or function by function, and you try to think about, well, this function, and well, there's a control, there's an input, there's a resource, there's an output. When will this happen? What happens if there's variability in the inputs, and so on? And you can do that for a simple model. You can do it mentally. You can discuss it with your colleagues, and you can sort of make what's called a walkthrough of the model, and satisfy yourself that it is probably going to work as you think. But if you take the one here on the right-hand side, a more complicated model, it becomes more difficult to do so. And we cannot really check whether this is going to work or not. But it would be really nice if we could say, yes, this will work, or no, this will not work, but I also know why it will not work. So the question is, how do we do that? In the FRAM model visualizer software itself, which I assume that most of you will be using, there are built-in checks which you know that you have some of the aspects are marked with a red ring, and they are orphans. And they're orphans, which means that they're only defined for this function, but not for another function, which means that they're not linked to it. So here, obviously, the input is not linked to anything, which means that that doesn't make sense. Of course, there must be an input to a function. Here it means that there is a resource. There are two resources that are described, but there's a third resource that isn't described, and the red dot indicates that. So this is what the FRAM model visualizer does at the moment. The FRAM Model Interpreter, the FMI, tries to do something in addition to that. One thing that is that it tries to look at entry functions. And an entry function is a function like this. It's a background function that provides an input to another function, which means that this is what starts the model. This is what starts the activity. And in this case, there's only one entry function, because there are other background functions, but they do not provide inputs. They only provide some of the other aspects. There are exit functions, which are background functions that receive their input from a foreground function. And when you get to this and activate this, then the activity has come to an end. That's why it's called an exit function. So the FRAM Model Interpreter will check for entry functions to make sure there are some. They will check for exit functions to make sure there are some, and it will check for auto loops. And an auto loop is, of course, you can have loops, you can have connections between functions, but an auto loop is a function that connects to itself. There are no examples of it in this slide because it's bad. But for instance, if this function, if this output from this function was a precondition to this function, that would be an auto loop. And that would mean that the function would never start, of course. So we look for auto loops and try to identify them because they are incorrect, syntactically incorrect. So when we talk about models, of course, and that's one very important part of the FRAM, to be specific about what models are. And usually in your daily life, in your research and in practice, and we see that in newspapers, even people talk about models of this and models of that. Politicians have model about the economy. Epidemiologists have models about the pandemic, and models about how shutdowns or lockdowns will work and so on. So we tend to talk about models a lot. And usually when you see people talk about models and then they may come up with something like this, a simple diagram which shows there are some entities and they are related, or a more complicated diagram like this with lots of arrows and lots of things, and it looks very impressive, but we don't really know what it means. So if you go back to and think about what a model actually is, then I found a very good definition here by Coombs, Davis, and Tversky about 50 years ago. And they say the basic defining characteristics of all models is the representation of some aspect of the world by a more abstract system. In applying the model, the investigator identifies objects and relations in the world with some element and relations in the formal system. So the point is that the model represents what you are trying to deal with in a more simplified form, so that it is amenable, so it's possible to analyze it, to test it, to do what-if scenarios and so on. But it's a simplified representation of something that exists in the real world, something that you're interested in, as in the work that is normally done with models. That means that a model must be based on some principles about how the real world works. And because without that, you can't build the model. And as you know, in the FRAM, we have 4 principles. We have the principle of equivalence, of successes and failures. We have the principle of approximate adjustments, which describe the variability of functions. We have the principle of emergence, that things can emerge not by a cause-effect relation, but in other ways. And we have the principle of functional resonance, which means that you can have nonlinear consequences of variability. They can build up through emergence in the model. So the FRAM is very explicit about the principles it's built on. And it also has, as you know, it only has very few components. It has the functions, the couplings, and the aspects. So with that as a background, how can we then make sure that a model is correct? Well, one way of considering it is to say that a model, a function is actually can be seen as an agent. It can be seen as something that is active and something that does something. And if you take a model here, and I've taken one of my friends in Brazil has made this figure that he calls a framigo in Spanish. I mean, amigo means friend in Spanish, so he calls it framigo, which is a joke. But you can look at it as if it was an agent that he looks at and says, are my inputs present? Is there anything about time that affects me? Are there any controls? Are my preconditions here? Do I have the resources I need? And if it is so, if my inputs are present, if my preconditions are present, if the resources are present, if time information is as it should be, if the controls are okay, then I produce the output. But you can look at every function as an agent that sort of constantly evaluates the state of the aspects. And when the state of the aspects is according to the specifications given by how you describe the function, then it produces the output. So a FRAM model is, of course, not a flow model. And I think it's important to say that there's no flow in the model except during an actual instantiation. So let me illustrate that. Here is a function. This is the very simple model that some of you have used and that I actually learned when some years ago when I had a small training course in Japan of making cup noodles, making delicious cup noodles. And one function there is to remove the lid. And it just says remove the lid, and there's an input that says that the noodles are tender. They have been soaking in boiling water for 3 minutes, so now they're tender. Then you remove the lid, and the consequence of that is that the lid is removed. But you can rewrite it as a bit of software, a bit of a program. So the function is to remove lid, but you can write it formally in this way. If noodles are tender, which is the input, then remove lid. Otherwise, wait, means do nothing. So it's a bit of code. So this is what the agent does. It continually evaluates that code. And if the noodles are not tender, it waits. If they're tender, then it removes the lid. Let's take a little more complicated example here, where you have to remove lid, the same function here, but you have another function, which is to stir carefully, which is actually the next step. So you remove the lid, and you have to remove the lid before you can stir carefully. In both cases, the input is that the noodles are tender. But if you look at this function, then it says, if the noodles are tender and If the lid has been removed, which is a precondition, then stir carefully, otherwise wait. So it doesn't start, you don't start to stir carefully the moment the noodles are tender. You have to wait for the lid to be removed. So it's a conditional statement. It's a little more complicated conditional statement, but the point is that you can actually try to look at functions and say, well, each function represents a set of statements about the world, and these statements can be evaluated or executed, and that's why the functions can be understood as agents. So basically, we can see that all functions, all foreground functions, because background functions don't do anything. They're just there. They don't change, they're not variable. But all foreground functions represent a set of instructions. And we call these instructions the implicit method of the function. So you can see the whole model as a set of methods, a set of instructions, and therefore as a program. So you didn't know that, but when you build a FRAM model, you're actually writing a program. You're writing a program that describes an activity. So we can also, and we are working on that, add specific methods that are not given just by defining the function, but you can actually write other methods, other parts of code that are added to the function. But I'm not going to talk about that today. This is work that is in progress, and perhaps next year or in 2 years, we will have something to say about that. But let me stay with this here, the simple way of looking at functions as code, as software. So the idea is if all functions, all foreground functions can be seen as a bit of code, a bit of program, then we can also say that, well, in the model, all functions, all foreground functions continuously evaluate the status of the aspects, input, preconditions, resources, time, and control, to see if the aspects are present. And the aspects are, of course, like in this case, generated by an upstream function. So it's only when this upstream function is activated and produces the output that this function that can be activated. This is a dependency. So you could say that instead of having a flow through, then in parallel, all functions will look at the environment and say, are my aspects present? If the aspects are present as specified by the function, then the function is activated and produces its own output. So whenever, in this case, whenever the input is present and the control is present, then this function will generate its output, and therefore this function can be activated and generate its output, and therefore another function can be activated, and so on. But if this is not present, or if this is not present, then this function is not activated, and the following functions will not be activated. So in principle, all functions look continuously at the status. So in principle, the interpretation is parallel, but it's also asynchronous because we don't have any real time that we can talk about. But it's not sequential, it's parallel. That's quite important. So it goes through cycles. In programming, you can't really have a massive parallel execution. That would mean you need a processor for each function. So what we do in principle instead is we go through cycles, and in each cycle you evaluate all the functions. I'll show you how this is done. Another important thing, of course, is the variability, and this is an important aspect of the FRAM, that functions can be variable. There can be variability of functions, which means that the output is variable. The output can be variable with regard to time, or it can be variable with regard to precision. And it can also be variable in other ways, but time and precision are the ones that are most typical that are found most often, and these are the ones that we at the moment now can represent directly in the FRAM model visualizer. The variability of a function can have two different bases. One basis is that the function itself is variable. The nature of the function means that it is variable. We call this endogenous variability. Well, if you take a function that describes something a human does, then we know that humans are variable. They don't work as machines, but they work very well. But there is some variability, sometimes because of external influences, distractions, or so on. But sometimes internally, as you know, that your attention suddenly wavers, or suddenly you find yourself thinking about something else because something comes up in your mind, and we don't really know how that happens. We only know that it happens. So there is the internal variability, but there's another variability which is also important, or perhaps more important. This is the variability that comes from upstream functions. If there is variability in a function, then the output will be affected. And the output will then be an input, a precondition, a resource, a time, or control for other functions, for downstream functions. And if the input to any of the aspects of a downstream function is variable, then of course that will affect the function itself. That will also become variable. And this is how variability spreads through the model. The upstream-downstream relation is called the exogenous variability. At the moment, in the first version of the FMI, we represent the internal variability of functions, but not the variability that comes from upstream functions. That is work that we are working on now, and this will come in the next version of the FMI. So let me give you an example of how the FMI works. This is another model this is a model of a ferry that's leaving harbor. So the function is to leave harbor. And you can see the inputs are that the harbor stations are manned, which means that people on the ferry are in the positions where they should be when they start to sail. The vessel has to be trimmed, which means you have to balance with the load. This is a car ferry, so you have cars coming on board, and you have to balance the trim of the ferry afterwards so it sits correctly in the water. You have to close the bow doors, of course. You have to drop the moorings. There must be a loading officer on the bridge. There must be ship standing orders. This is the procedure. And if all this is in case, if the input is there, if the preconditions are fulfilled, if the resource is there, and if the control is there, then the output will be activated. So you can write it like this. The general term, the general version of it is this: if all defined inputs are present, and if all defined preconditions are present, and if all defined resources are present, and if all defined times are present, and if all defined controls are present, then the function is activated. Otherwise, it waits. For this specific function, the code will look like this. If harbor stations are manned, which is the input, and vessel is trimmed, which is a precondition, and bow doors are closed, which is another precondition, and moorings have been dropped, which is another precondition, and loading officer is on bridge, which is a resource, and ship standing orders, which is a control, then the vessel has left harbor. Otherwise, wait. Now, the point is that the FRAM model interpreter can read the function that is produced by the FRAM model visualizer, and the FRAM model interpreter itself automatically generates this code. You never see it, but it's generated automatically in the evaluation of the function. And this happens for other functions as well. So this is what it looks like. In the first version of the interpreter was a text-only version where you just had a little display on the screen, and you couldn't see the model, but you could manipulate the model. But there have been some developments since then that I will talk about. But as I said, this is the strict interpretation, which is that it considers all the inputs and all the aspects. So it doesn't consider variability in any sense. There is no variability in this. This is a strict logical interpretation. Sorry. But you can have a variable interpretation, and you can vary the interpretation by selecting a function. And in this case, we select the function leave harbor. And when you select the function, then a little window comes up like this. And in this window, you can indicate for inputs whether the function should consider all inputs or any inputs. Now, in this case, there's only one input. So it'll have to be all, or all or any means the same. If you look at preconditions, however, there are 3 preconditions. So you can actually say, should the function look at all preconditions, which means that all 3 preconditions must be true? Should it look at any preconditions, which means that if just one of the 3 is present, then this is considered to be present? Or should you select none, which means that it disregards the preconditions completely? And this, of course, is a variability of the function. You can say, well, if you have plenty of time, you look at all the preconditions. If you have little time, you just look at one. Or if you're in a big hurry, you skip them all together. The same with resources, except in this case, there's only one resource. The same with controls, except in this case, there's only one control. But notice there's no selection for time because there are no time aspects. So this window will show for each function which of the aspects you can choose from. You can also select whether you want to look at all the aspects. In this case, there are 3 aspects, or only look at some of them. So this is even more variability. You can say, well, if the input is there, do I look at everything else, or do I just look at some of them? And some is a random selection. So it could be at some time you just look at the control, at some time you just look at the resource, at some time you look at the preconditions, or maybe you look at 2 of them. At the moment, this is a random selection. But what you can do in this way is you can go through the model, and for each function you can, as you select here, there are 5 functions in this model. You select the profile, you define the profile, save the profile, and then you go out, then you start to execute the function. So as I said, this is just to show it more clearly, you can set the variability for each aspect, or for any aspect that you would like. And you can also select whether you want to consider all the aspects or just some of them. And again, some is at the moment implemented as a random selection, a stochastic selection, but we're working on that to make it more controllable by the user. So as I said, the FRAM model interpreter is a text-only version of it. and this is a screen that you see towards the end of the presentation. I'll tell you where you can find the FRAM Model Interpreter. It's free. You can just get it and use it. You have a screen like that. You of course you select the model file, and it will read any model that is produced by the FMV. So the output file from the FMV is the input to the interpreter. You will then have to initialize the model, and the initialization serves to identify entry functions and exit functions. It checks that the syntax of the model is correct, and it checks that there are no auto loops. So it's a formal check of the syntax of the model that tells you, yes, this model is syntactically correct and it can be executed. It can be interpreted. If any of these are false, if there are no entry functions, if there are no exit functions, if the syntax is incorrect, or if there are auto loops, it cannot be interpreted and the interpreter will stop. So this is a first simple check of the model, which again, if you have a simple model with 5 or 10 functions, you can do this by hand. But if you have a complicated model with 20 or 40, or we have even had models with 100 functions, it's impossible to do this by hand. I mentioned entry and exit functions, and here I describe them in a little more detail. The entry function is a background function. BG stands for background. A background function where the output is the input to a foreground function. So basically, when you start, because background functions are not variable, they're always producing the output. So there will be an output here. So you can say that the interpretation of this model starts here by, this is again the cup noodles example, by adding boiling water until the fill mark. So boiling water is present, and this starts the evaluation of this little model. And again, the model evaluation ends when you reach this point, which is what you wanted to reach. You have the delicious tender noodles and you are ready to eat them. But there can be more than one entry function, of course, and there can be more than one exit function. And the interpreter will check if they are there, and it will also check as you interpret the model, as you go through it, cycle after cycle. When it comes to a point where all the exit functions have been fulfilled, when all the exit functions are active, then the interpretation will stop, because then you have come to the end. The way you run the interpretation is fairly simple, but of course you want to document this, and the way you document it is by selecting a session log, and there are two types of logs. There's a standard log, which contains all that's on this pane will be written in a simple text log, as well as and it'll be done for each cycle of the interpretation, so you can step by step follow through. You can have a more detailed log, which does the same, but also for each cycle, it provides a description of all the functions and the status of all the aspects of all the functions. So it's quite an extensive log. But it's very good when you want to debug a model and want to see how it developed and understand why something happened, or sometimes understand why something didn't happen. So you need to define the log, and then what you need to do to start, you simply click, there's a menu here, you begin the interpretation, and then you use this to go through. So this is the first step, the initialization, and then you go through and step by step through the interpretation. And what you see is this. this is a lock. You say, it says begin initialization. The enter function is finish loading. This is the ferry example again. The exit function is start C passage. So it says model initialization is complete. The model is okay. You can begin to interpret it. And then it simply shows here, cycle by cycle, the functions in each cycle, which functions have been activated. In the first cycle, 2 functions were activated. In the second cycle, 2 other functions were activated. In the third cycle, 1 function was activated. And in the fourth cycle, the exit function was activated. And it says all exit functions have been activated, and therefore the interpretation stops. So let's look at this example in a little more detail. This is actually the ferry. Some of you may know there was a terrible accident many years ago with this ferry, but the model is not a model of the accident. The model is a model of the successful departure of the ferry, because until the accident happened, all departures were successful, and that is the idea of safety 2 and FRAM. We need to describe how things work as a basis for understanding how it didn't work. So again, you have the entry function here. Loading is finished. You have 1 background function, which is the company rules, ship standing orders, and you have 1 exit function, which is you start the C passage. So once you have gone through this, you start the C passage and you reach the end. The interpretation comes to an end. So what it does is simply it just identifies enter function, exit function. In the first cycle, it says trim vessel has been activated, this function, and then also man harbor stations have been activated, this function, because they're both activated by the enter function. In the second cycle, closed BODAS is activated. This is this function here, and this becomes activated because this has been activated previously, and this precondition is also provided both by the background function and by this function here. Drop moorings has been activated. Drop moorings is here. And again, it's because the input to this function was generated in the previous cycle. In the next phase, leave harbor is activated, and this is activated because in the previous phase, this was activated, and this was also activated, and this was activated and provided the precondition, just as this one provided the precondition. So this activates this function, and in the last cycle, this function is activated, and the ferry leaves. So everything works. Now we know that in practice, this didn't work because we had the accident. And we can look at it in this way and say, well, what actually happened was that in the leave harbor function, they didn't check all the preconditions. They only checked some of the preconditions. Let's go back and say, to leave harbor, there are 3 preconditions. The vessel is trimmed, the bow doors are closed, and the moorings have been dropped. In the actual case, they didn't check all the preconditions. And as a consequence of that, this function is activated too early. And as a consequence of that, when you reach the exit function, the situation is not as it should have been, and that's why in this case things went wrong. But this is a way of showing how you can illustrate the accident, because you can go into, in fact, you can go into any of the functions here and set the variability of how the aspects are evaluated and then you can run the interpretation and you can see the consequences of it. So the interpreter is a kind of what if tool. It says, what if there was variability here? What if this resource was not present? What if all the preconditions were not considered? And you can specify that function by function. Of course, it will take, you have to go through many cycles to check everything. But you can define the most characteristic conditions that you want to look at. You can specify them in the model, and then you can run the interpreter, and the interpreter will show what the outcome is in the FMI log. That is a consequence of that. So this is what the interpreter does. And of course, people would say that, yeah, this is very nice, but wouldn't it be lovely if you could actually see it? And of course it would be. So what has happened is that the functionality that has been specified by the FRAM Model Interpreter has now been included in the FRAM Model Visualizer. Except, I should say straight away, the visualizer, this is not in the freely available visualizer. This is only in the pro version of the visualizer. So unfortunately, this is not free. You have to, there's a charge for it, but you get the same functionality without the graphics in the FRAM Model Interpreter, and you get that for nothing. So, but let me just look the same simulation again as it looks graphically. In the first cycle, you identify the entry function and the exit function and the background function that produces in this case, the controls. In the second cycle, these two functions are activated exactly as here, that these two functions are activated. But now you can see it graphically. In the third cycle, these two functions are activated. In the fourth cycle, this function is activated, and this ends the interpretation because then you activate the exit function. So this allows you to see step by step how the model progresses. And of course, you can also specify the variability. You have what we call the interpretation profile, which is exactly the same as for the text version, except that you cannot choose whether you want to look at all the aspects or only some of the aspects. So you only have the possibility of indicating the variability of the individual aspects. But you can do that, and then if you run the model again, you can see here you have the first, in the cycle 2, you have the same, these two functions are activated. In cycle 3, these three functions are activated, which normally would normally happen only in cycle 4, but because of the variability you have specified here, that it looks at any precondition instead of all preconditions, it becomes activated too early, and the ferry leaves too early. So this is even this model here is fairly simple, the hell of free enterprise, and you could say in principle, well, we can go through that hand by hand. But let's take a more complicated model like this. This is a model of the outbreak of the MERS, Middle East Respiratory Syndrome, in South Korea in 2015. And you can sort of say, well, if you want to go through this model and see whether it works or not by hand, this would be very difficult. And you would probably have a lot of discussions with the people who were there. What happens with this function? What about this? And what are the consequences and so on? And even this is a fairly simple model. But we can do this in the FRAM model interpreter again. And I'll just show you what it looks like in the text version. Here is the same model again, and here's the lock. There is one exit function. There are two entry functions. Actually, there are many entry functions and there are many exit functions. I cannot even count them here. And you go through the interpretation cycle. Again, this is the model we're looking at. You go through the interpretation cycle, cycle 1, cycle 2, and then cycle 3. And then after cycle 3, you get this message: no functions were activated during the cycle. The interpretation cycles end. So what this shows is, if you start to go through the model, then in the third cycle, it stops because it cannot get any further. So even though the model looks nice and it seems to be reasonable, there are no orphans or anything, it doesn't work. So, and you can go through that, then you can go through your log and you can find out why it doesn't work. If you have the FMV Pro version, you can also run it there. And if you run it in the FMV Pro, you see it will stop here. And the reason why it stops here is fairly obvious now that you understand it, because this function has an input that comes from a downstream function. But this function is not activated until this function is activated. So it will just wait here. This function cannot be activated until this is activated. So this function will never continue. The model will never continue from here. And the same goes from here. This function has, as you can see now, an input that comes from a downstream function, and it will never be activated. So the model will stop here, which means that the model is not correct. The model is not, it doesn't work as it should. And again, if you go back and you look at the normal rendering of it, it's very, now that we know it, of course, we can find these, but it's very difficult to find these. But both the FMI, the text version, will identify where the problem is. And it'll tell you where you stop and why you stop, because you can look at the detailed status here and see what has happened. And of course, the graphical version will make it even easier. You can see that. The problem is this works fine, but if you have, say, 60 functions, then even this becomes difficult to see. That's why the text version, even though it is a little more difficult or laborious to use, will in principle be applicable to all the models you build, no matter how big they are. There's no limitations in the FMI. So to summarize, we can use the FMI, the FRAM Model Interpreter, to check, first of all, the formal correctness of a FRAM model. Not just the orphans, but the full formal correctness, whether the syntax is correct. It can show how functions become activated during an instantiation, and therefore it can show how an instantiation develops. It can also show the basic forms of variability of functions in how aspects are evaluated individually, and in the text version also how aspects together are evaluated. That's not present in the graphical version at the moment. As I said, we only look at the endogenous, the variability of the function, but we're working on developing the next version where you also can include the upstream, downstream variability, and you can also begin to specify variability in terms of time and precision, so that you get even greater control of how the interpretation takes place. So it's basically a kind of what-if simulation of the model that you can use to explore the situations. And And this is, again, the purpose of the model. A model is a simplified representation of something that you are interested in investigating that makes it possible for you to investigate it, whereas it would be impossible in the real life version. So that is the work that has been going on. We think it's an interesting step forward in the use of the FRAM. There have already been some examples of how this has of using this and to enhance the understanding of the models that you make, of the situations that you analyze. For practical information, you will, I think you already have, or you will get these slides, so you have the information here. But the text-only version of the FMI is a standalone version, which is available for Windows and for Mac, for Mac computers, also for Linux computers if you want that. It reads the XFMV file produced by the FMV and interprets a model, and you can find it here. And you can just download it, and it's a standalone installation. The same functionality, nearly the same functionality, is also integrated in the FMV Pro function. For this, to use this, you need a license, and you can find information about the Pro version and the license by looking at these websites. So with that, I've come to the end of what I wanted to tell you about. We are all very excited about the FMI, and I hope you'll find it interesting. And if you want to try it out, please do. If you have any issues or questions, you are very welcome to contact me, and I'll be very happy to try to help you with that. So let's see, let me go back to where you see.
Thank you.
We'll get out of this.
Please, yeah, keep it displayed.
Oh,
like
this
that.
one, sorry. Yes, stop sharing. Right.
It's okay.
Sorry.
Okay. Thank you very much, Dr. Hollnagel.